problems. And those are problems of the following type. We have an algorithm which is given a set of samples drawn randomly from some unknown input distribution D. Although we might know that this input distribution D belongs to some family of distribution over the input domain X. For example, we may know that this is a mixture of some two Gaussians. And the algorithm needs to figure out something about that distribution. For example, it might want to know some property of that distribution, some parameter of the distribution, or might want to solve a prediction problem over this unknown distribution. So a classical type of this problem is the pack learning model, in which the goal is to learn some class C of Boolean function over some domain Z. So a sample from an input distribution in this problem is just a label example, which consists of a point and a label, where point is drawn from some distribution P over this domain of the function, and label is determined by some function from this class of functions. And the goal of the algorithm is to output some hypothesis H, which predicts the label with probability at least 1 minus epsilon on an example drawn randomly from the unknown distribution T. So as I mentioned, we'll be looking at restricted classes of algorithms for solving these general statistical problems. So, and the main restriction we'll be looking at is referred to as a statistical query model. And this model, instead of the algorithm, instead of having this random sample from the input distribution D, has access to a statistical query oracle for the distribution D. So the algorithm can ask queries, where each query is a real valued function over the input domain. And as a response to that query, the algorithm gets some value V, which estimates the expectation of this function on a sample drawn randomly from this distribution D up to some parameter tau, which is referred to as the tolerance of the query. And it roughly corresponds to the number of samples in the original model. Okay, so at a high level, there are two reasons why we're interested in this model. Okay, so let me say that it can ask more than one query, as many basically as it needs. And at a high level, there are two reasons why we study this model. The first one is basically it's a kind of an abstraction of the information that an algorithm might want to have about the input distribution. And once you express your algorithm in this abstract model, you can then implement it in other models of access to data, which satisfy some additional properties or have some or constraints. For example, one can obtain noise-tolerant learning algorithms through this model. One can obtain differentially private algorithms which work in the distributed model of access to data, and so on. The other reason for study of this algorithm is some interesting properties of the statistical query complexity, which is the complexity of solving problems in this model. So the first property of this notion is that most techniques which are used for solving these various statistical problems have analogs that can be implemented in this model. So it's a very powerful sort of notion of complexity. And at the same time, it's possible and often not too hard to prove lower bounds against algorithms which are implemented in this model. So by combining these two facts together, we get we basically get some sort of proxy for the computational complexity, which is of course extremely hard to analyze, where the number of queries roughly corresponds to time, and the tolerance roughly corresponds to the amount of data that the algorithm has. So in this work, we'll be looking at a generalization of this model, a very simple one. It's called k-wise statistical queries. So in this generalization, an algorithm has access to k-wise statistical query oracle. And a k-wise basically means that now the functions, the query function will depend on k samples. And in response to this query, the value that the algorithm will obtain is the expectation of this function on k samples, each drawn randomly and independently from the input distribution. So the algorithm can look sort of at k samples at a time. And you can think of this algorithm, of this sort of extension, as interpolating between the regular unary model and the and these general algorithms, which are unrestricted and can see all the random examples at the same time. So for more concrete examples, for example, a collision probability is a typical you can think of it as query in this model, because a collision probability is a probability that two randomly drawn samples are equal. and that sort of requires looking at 2 random samples, estimating some sort of probability or expectation over 2 samples. And slightly more sophisticated examples come up in hardness amplification, where one converts a problem over sort of learning a single function to a problem of learning some function that combines k independent instances of a learning problem. So the question we would like to understand is very simple. Are these k-wise queries more powerful than their unary queries, and sort of by how much? And it's a natural question. In fact, it has been asked already back in 2000 by Blum-Kalam and Wasserman. And they considered this question in the context of packed learning, where the distribution over the domain of functions is fixed to some distribution p. And in this context, they showed that k-wise queries are they can increase the power of the model by a factor of at most 2k. Both in the number of queries and the tolerance. So basically, if there is a class C that is learnable in the setting with q queries of tolerance tau, then there is k-wise queries of tolerance tau. Then there is an algorithm which will learn the same class using 2 to the k times q queries to the unary oracle with tolerance which is higher by a factor of 2 to the k. So we are interested in this problem in this more general setting of problems over distribution, and in particular also learning without restricting the domain of the functions. And we show that in this more general setting, the picture is more complicated. Sort of as a first step, we show that in this more general setting, increasing the arity of your queries by 1 can already increase the power of the model exponentially. Specifically, there exists, for every k and n, there exists a class of function C that is learnable sort of efficiently in time using polynomial number of queries to k-wise oracle with inverse polynomial accuracy. But if you only have k minus 1 wise queries, then you will need an exponential number of queries, even if those queries are of exponentially low tolerance or high tolerance. So basically, this shows that in more general setting, one cannot have a strong upper bound on the power of k-wise queries, but maybe in some interesting special cases one can, and that's what we showed, that there are some interesting cases where you can bound the power of these queries. So the first one, reduction, basically the reduction from k-wise to unary queries, we show that it is possible to exploit the structure of the class of the distribution that we have. Specifically, if the class of distribution over which we need to solve a problem is gamma flat, where gamma flat means that there exists some reference distribution such that relative to that distribution, all the densities in the class of our distributions are at most are larger by at most a factor of gamma. So if this class of distribution is gamma flat, then a k-wise query can be simulated using this roughly gamma to the k, relatively large but number of queries, to a unary oracle but with tolerance which only grows, sort of increases linearly with k, which is kind of optimal.
Vitalik,
yes.
How come d0 doesn't appear in the statement of the theorem?
Yeah, it doesn't matter. You will use it, but it doesn't matter. I mean, you only need that there exists one, and you'll be using it in the reduction.
1 minute.
Okay. Yeah, okay. So one interesting case of these distributions is that this packed learning that I mentioned with the fixed distribution is actually just too flat. So this result generalizes the result of Blum-Kalam Wasserman, and also strengthens the tolerance exponentially. Their tolerance grew exponentially with k, and that's important for some application. So the second reduction that we showed, that it's possible to exploit the sort of simplicity of the query function itself. So if a query function has k party randomized communication complexity of at most p bits per party, then that specific query can be simulated using a small number of queries, but of tolerance which grows exponentially with the number of bits that are needed. So both of these reductions are relatively simple, but they build on some recent advances in understanding of statistical queries for these general problems. The first reduction builds on a work of mine that gives a generalization of statistical query complexity of solving general statistical problems. And the second one builds on a stronger connection between statistical queries and algorithms that extract small number of bits by Steinhardt, Valiant, and Wager, also from the last year. So let me briefly mention some corollaries.
I'm sorry, you're out of time.
Okay. So let me just one more minute. Okay. So one corollary we can get is that we can now get lower bounds against these k-wise algorithms for much larger k's. For example, for the famous problems of learning DNFs and stochastic constraint satisfaction problems. And the second type of corollary is that we can, for example, show that collision probability can be estimated within tau using just 1 over tau square queries to this to the oracle with polynomial dependence on tau intolerance. It's relatively it's not so easy to prove directly, but in our case, just follows from equality having smaller randomized complexity. So let me just so we have some implication for related models. Since I don't have much time, you'll just read. And one natural open problem is whether there is a general approach that will unify these two reductions. Again, sorry for
question while Javier is setting up.